a video on computing definite integrals. So we can see here we've got basically a theorem, the fundamental theorem of calculus pretty much, that says if we have a continuous function, so a function that has no holes, no breaks, no vertical asymptotes on an interval, closed interval, and we have any antiderivative of that function on that closed interval, then we can define this definite integral. So the way that this is written, this is called the definite integral of f of x from a to b is equal to that antiderivative, and then we use a notation to still remind us we still have to plug in the upper and lower limits, and the order that we substitute them and subtract them are specifically this order. So let me just talk briefly here about these numbers here. So really, it's kind of like when we were looking for a max or a min on a specific interval. It's sort of this idea that, we can find value for this antiderivative over this interval. And we'll talk in the future about what are the applications about this, or you can watch other videos that talk about the application of definite integrals to calculate areas and surplus and all sorts of other things, average value. So anyway, the b up top here is called the upper limit. And this is not a limit in the sense of like, what is the limit as x approaches 7 of this function, but limit as sort of like it's our end point, right? We're going from left to right in this point. So upper limit, so that's our right end point. And then this number down at the bottom is going to be called our lower limit or left end point, right? So upper limit is going to be your right end point, and the lower limit is your left. So to remember that order, basically that's how you're going to remember. Lower and left start with the same letter. So now we have any antiderivative, we're calling it capital F here, and then to indicate that we're not done, that we need to do more work, that this is different than just a plain old indefinite integral, we use that long vertical bar and still keep A at the lower limit and b as the upper limit. And we put the bar at the back so that it doesn't get confused. And I'm going to write something in here and then erase it. But notice if we put it out in front, it might sort of, if you're not careful, look like another integral symbol. So we would think that, oh, I have to integrate again, and we don't. So that's why this vertical bar goes at the back, so it's not confused for another integral symbol. And then we're basically going to plug in the upper limit, the top number, and the bottom number, and then we're going to subtract them in that order. So top minus bottom, or upper minus lower. Right? So always in that order, and subtraction order matters. Okay. So we're going to go ahead and we're going to do some examples. I've got 5 of them prepared for you. So let's go ahead and take a look at the first one. Okay, so the first one is the definite integral of 3 with respect to x over the interval from 2 to 7. So first step is find the antiderivative. And notice in the theorem it says any antiderivative. So it turns out we can leave off the constant of integration c. For 2 reasons. One, because it says any antiderivative. Well, okay. Well, if we choose the antiderivative where c is 0, that will do the trick. And the other reason is that, let me go back, that remember when you have f of b minus f of a, well, if they both have the constant in them, they're going to subtract off, right? So we can go ahead and leave off c. Step 2 is plug in the upper and lower limits into the antiderivative. And then step 3 is subtract top minus bottom, or upper minus lower. Okay, so we're going to follow these instructions. So first thing is find the antiderivative. So find the function whose derivative is 3. So any linear function, 3x, or 3x plus 7, 3x plus 0, 3x minus 11, any of those would be an antiderivative. So we're going to choose the one where c is equal to 0. So we're going to leave off the c. All right, and then we draw our vertical bar at the back to indicate there is still work to do. And one thing I like to do to make my life a little easier here and that I make sure that I don't have any confusion with signs is I go ahead and I say, okay, when x is equal to 7, then we get 3 times 7 or 21, and then I write that down up here. Then I figure out, okay, what is x? When x is 2, then we get 3 times 2 is 6. So minus 6, and that answer is 15. So this is really the reason why it's called a definite integral. You get a definite answer, right? There's no variation. There's nothing that's unsettled. There's nothing that's indefinite. This is definitely a definite answer, right? 15 is about as definite as you can get, right? All right, so let's try another one. All right, here is a polynomial. So we're looking for the antiderivative, or we're evaluating the definite integral of 3x squared plus x minus 2 over the interval from 0 to 3. So remember, step 1 is just find the antiderivative. So the antiderivative of 3x squared, I'm going to use the constant multiple rule and then use the power rule for antiderivatives, the sum rule for antiderivatives, and then remember we can leave off c because we can choose the one where c is 0 in this case. And if we clean that up, 1/3 of 3 is 1, so this is x cubed plus 1/2 x squared minus 2x from 0 to 3. And again, this is where I find it helpful to just go ahead and compute what this is, right? 3 cubed minus plus 1/2 times 3 squared minus 2 times 3. So it's going to be 27 plus 9/2 minus 6. So it's going to be 21 plus 4.5. So that's going to be 25.5 minus, and when x is 0, what do we get? We get 0 cubed minus plus 1/2 times 0 squared minus 2 times 0 is 0. So 25.5 minus 0 is 25.5. Right? So I like to calculate it out individually and then plug them into the final answer so that I make sure I don't make any mistakes. Now I know this one was 0, but if I, did minus, I'd have to make sure to change all of the signs of whatever is in that computation, right? So I like to just calculate them up separately, figure out what they each are separately, and then do the subtraction. Okay, let's try the next one. All right, x to the 3/2. Should be, 3/2. We're going with that one. Okay, 3/2 plus x to the 1/4. All right, so first things first, find our antiderivative. So x to the 3/2 plus 1 is going to be 5/2. Dividing by 5/2 is the same as multiplying by 2/5. Plus x to the 1/4 plus 1 is going to be 5/4. Dividing by 5/4 is the same as multiplying by 4/5. And again, we can leave off c because we're choosing c to be 0. Or if we had plus c, when you subtracted these two things, both the c's would subtract off, right? You'd have c minus c, which is 0. All right, so let's go ahead and figure out what we've got here. When x is 4, we've got 2/5, 4 to the 5/2, plus 4/5, 4 to the 5/4. So let's see, that's going to be square root of 4 is 2. 2 to the 5th is 32. 32 times 2 is 64/5. Minus, let's see, the 4th root of 4. Or this is, 1 and 1/4. So we've got a 4, so that'll be 16/5 times, we've got 1 4 left behind, 4 1/4, 4 to the 1/4. So this is 64 plus 16, 4th root of 4, all over 5. And then when x is 0, what do we get? 2/5 times 0 to the 5/5 plus 4/5, 0 to the 5/4, which is 0. So this result is 64 plus 16, 4th root of 4 over 5 minus 0, or 64 plus 16, 4th root of 4 over 5 for my final answer. And again, right, make sure that you're paying attention to whether or not we have being asked about giving an exact answer. This would be exact. And then if you plug this into your calculator, you would get an approximation and have to round. Okay. Now I know in each of these cases I'm plugging in 0 and we get out 0, right? But I want you to be careful here because not in every case are you going to get out 0. And we'll see that if you exponential functions, right? If you input 0, you don't get out 0, you get 1. So we have to be careful there. All right, so this next one, find the antiderivative. We've got 2 over x. We can think as 2 times 1 over x, right? So the antiderivative is going to be 2 natural log of x. Using the sum rule, 3x, because the derivative of 3x is 3. And then from 2 to 4. So when x is 4, we get 2 ln of 4 plus 3 times 4. So that's 2 ln of 4 plus 12. 2, whoops, make that look more like a 2. 2 ln of 4 plus 12. And then when x is 2, we get 2 ln of 2 plus 3 times 2, which is 2 ln of 2 plus 6. Okay, now I'm going to go ahead and because I'm noticing I've got this ln of 4 here, that I'm going to use the properties of logarithms that says if I have this 2 out in front, I can rewrite this as ln of 2 squared, right? It becomes an exponent there, which means ln of 4 plus 6. So this is minus ln of 4 plus 6. So this is 2 ln of 4 minus 1 ln of 4. That leaves 1 ln of 4, and we've got 12 minus 6 is 6. This would be my final exact answer. If we're asked to round, then we would plug this into our calculator to figure out what that would be. Okay. And then last but not least, we have an exponential example. All right, so first things first, find the antiderivative. Antiderivative of e to the x is e to the x because the derivative of e to the x is e to the x. And then minus e to the negative x, the antiderivative, well, we can think of that as e to the negative 1x. So the antiderivative of that would be 1 divided by negative 1, e to the negative 1x. Or if we're looking for what function would give me the derivative, let's see, this is negative e to the negative x. So I would have to compensate by making this negative to make this positive. So this is e to the x plus e to the negative x. Or you might be able to have reasoned that I'm looking for a function whose derivative is e to the x minus e to the negative x, and recognized, oh, because of that negative, if this was a plus in the middle, that would give me that result. So this is still from negative 2 to 2. So I'm going to do my same work here. When x equals 2, we get e to the second plus e to the negative second. And then when x is negative 2, we get e to the negative second plus e to the positive, right? Because opposite of negative 2 is positive. So this is e squared plus e to the negative second minus the whole quantity, right? So we have to be careful to subtract off the entire quantity, not just the first term, because then you won't get the right answer. So e squared minus e squared, e to the negative second minus e to the negative second, and in fact, that is 0. So hopefully you've got a nice selection of examples here to help walk you through how to do these definite integrals. Just remember those 3 steps, right? First, find the antiderivative, plug in the 2 values, and subtract top minus bottom, right? Whatever you calculate from the top value minus what you get from the bottom value, or upper minus lower. All right?